In this video, we'll look at the integrations of peaks in the proton NMR spectrum. And the integration, or the area of a peak, tells us how many protons exist in a particular chemical environment. And when protons exist in the same chemical environment, we say that they're chemically equivalent. So first, let's explore this idea of chemical equivalence in more detail. How do we know? How can we determine if two protons are chemically equivalent? Well, protons in a molecule are equivalent if there's a symmetry operation or a symmetry element that interchanges them. We've seen this idea with meso compounds in planes of symmetry, but here we'll see it in more detail with additional types of symmetry. Let's start with borane, BH3, as an example. Here I can rotate the structure by 60 degrees, and what I get is exactly the same as what I started with. So here a 60-degree rotation is a symmetry operation that relates each of the 3 hydrogens of borane. The 3 hydrogens are chemically equivalent. They sit in identical chemical environments. We'll also sometimes talk about symmetry elements, and the symmetry element is the axis of rotation. The operation is the act of rotating the structure, and the element is the point or line or plane that the symmetry operation is performed about. The most common symmetry operations that we'll see in the context of NMR spectroscopy are the 4 listed here. The first, a rotation about an axis, we just saw with BH3. The second is reflection through a plane. Here we'll use acetone or dimethyl ketone as an example. This molecule has a plane of symmetry that relates the 2 halves of the structure. The 2 methyl groups are chemically equivalent. They sit in identical chemical environments and are related by a plane of symmetry or a mirror plane. The third is an improper rotation axis. And this symmetry element is the combination of a rotation about an axis and then reflection through a plane. First, we rotate the structure, this alene, about the axis indicated with the arrow by 90 degrees. Then we reflect it about the plane indicated with the dotted line. So here your model kit may come in handy to visualize this symmetry. I highly recommend building a structure of this alene and relating the different methyl groups. Finally, the 4th symmetry operation is inversion. The corresponding symmetry element is an inversion center. And inversion is where we pass each atom through the center of the molecule to the other side. So the up OH group passes through the center and becomes a down OH group. A down bromine group passes through the center and becomes an up bromine on the opposite carbon. Now let's try an example. For each structure shown, predict the number of proton signals that will be seen in the proton NMR spectrum. This question is really asking us how many kinds of protons exist in each structure, because each kind of proton will give rise to its own signal in the spectrum. So here you really want to be looking for any symmetry that might exist in these structures. In the first case, there's a plane of symmetry that bisects the molecule. This makes the 2 halves of the molecule the same, meaning that the 2 OH groups are chemically equivalent and will give rise to the same signal in the NMR spectrum. I'll call them A. The 2 protons adjacent are chemically equivalent and will give rise to the same signal. I'll call those B. The proton that sits on the plane of symmetry is unique. I'll call it C, as is this one, D. And we can identify each different kind of hydrogen in the molecule and then tally how many kinds of hydrogen we have. Here we have 4, so this molecule will give rise to 4 signals in the proton NMR spectrum. And remember that although it looks like I'm labeling carbons here, I'm really labeling the hydrogens bound to those carbons. So if you need to draw them in to be sure you're assigning hydrogens, then please do. And this is an example of how we can draw in and indicate the hydrogens, denoting each as HA, HB, HC, etc. In the second example, I'll go through and assign hydrogens more quickly. And here I need to remember that there's free rotation around sigma bonds. So even though as it's drawn, all 5 hydrogens of the aromatic ring look different, the rotation equates the 2 halves of the ring. So on the left of the structure, the hydrogen indicated as A is unique. But these 2 hydrogens next to A are equivalent. They're related by the rotation around the carbon-nitrogen bond. And the next two hydrogens, the orthohydrogens, are also related by that same rotation. They're equivalent, and we call them C. This gives us three different kinds of aromatic hydrogens. Then we have the NH, and on the next carbon we have two hydrogens, and these two hydrogens of the CH2 group, or the methylene group, are equivalent. And then on the isopropyl group, this first CH is unique, and then both of these methyl groups are sitting in the same environment. They're chemically equivalent, and all of the hydrogens of those methyl groups are also chemically equivalent. So that gives us 7 different kinds of hydrogen, which will lead to 7 different signals in the NMR spectrum. In the last example, we have 2 planes of symmetry and only one kind of proton. So this structure will show only one signal in the proton NMR spectrum. Now let's come back to the integration values. The integration values, or the area under the peaks in a proton NMR spectrum, are always relative numbers. We may have a spectrum with really large or really small integration values, and that doesn't mean that a peak is coming from 200 protons. It means that we need to normalize the integrations. And to do that, we divide all of the integrations by the smallest value. In this example spectrum, the integrations shown are 7.96, 12.16, and 11.76. That doesn't mean that this peak is coming from 8 protons. If you try to draw a molecule that has 8 protons in the same chemical environment, that will be tricky. What this really means is that we need to normalize the integrations. And to normalize the integrations, we need to divide through by the smallest value. And here that's 8. So we divide each value by 8, and we get 0.99, 1.52, and 1.47. But we can't have 1.52 hydrogens in a molecule. Remember, these are integers. So we now need to multiply through by 2, and that will give us 1.99, 2.04, and 2.94. Now we need to note that integrations are also measured values, and so they often won't be exactly 2.00 or 3.00, but they will be more like 1.99 or 3.04. And we can round these values to 2 hydrogens and 3 hydrogens. These are now much more typical integration values for NMR spectra. We can also use this spectrum to review our chemical shifts. Remember that 1 ppm is a common chemical shift for alkane hydrogens, or hydrogens on sp3 hybridized carbons. The other 2 signals indicate that those protons are shifted downfield and are likely next to electron withdrawing groups, like an alkene, a carbonyl, or an arene. And in fact, this spectrum arises from methyl-ethyl ketone. The methyl group gives rise to the signal at 1 ppm. The CH2 group, or methylene group, gives rise to the signal at 2.4 ppm. And the methyl group next to the carbonyl gives rise to the signal at 2.1 ppm that integrates to 3 hydrogens. We'll end this lecture series with the question we posed at the beginning: to draw a structure that's consistent with the integrations and chemical shifts of the peaks in this fictitious proton NMR spectrum. And this is a fictitious spectrum because I've removed the coupling information so that we can focus only on the chemical shifts and integrations. Let's start with the integrations. These values are clearly too high to be describing the actual number of protons in a particular environment, so we need to normalize them. And when we do that, we get the values shown here. Here I can look at them and see that I need to divide through by 11, and I will get 5, 2, and 3. If you didn't see that right away, that's okay. You can follow the steps we learned for normalizing integrations to get to the same values. Now let's look at the chemical shift values. The signals around 7 ppm indicate aromatic protons, and there are 5 hydrogens, so that gives me a partial structure that's an aromatic ring with 5 hydrogens, or an aromatic ring with 1 group on it. The peak between 4 and 5 ppm is very far downfield, and so these protons must be next to something very electronegative. And when you see peaks around 4 or 5 ppm, These are very often protons next to an oxygen. Because the signal integrates to two hydrogens, this is a CH2 group, and it's next to an oxygen. Finally, the peak at 2 ppm indicates that this group is next to something like an alkene, a carbonyl, or an arene. It integrates to 3 hydrogens, and so this is a CH3 group next to a carbonyl, arene, or alkene. I'll call that X. Now my job is to piece together my partial structures. And here with this amount of information, there are some choices of how to do that. But we always want to start by finding our end groups, the terminal groups. And here the terminal groups are the arene and the methyl group. These have to be on the ends of the structure. And then we'll put in the middle groups, or the middle group in this case. And here I assumed the X group to be a carbonyl. But if I had more data, then that's something that I would want to look for. Like in an IR spectrum, I might try to confirm that there is in fact a carbonyl. So you can start to see now how these two spectroscopic techniques, IR and NMR, are complementary. The IR spectrum shows us the functional groups that don't usually have protons, and so not much information in the NMR spectrum, while the NMR tells us everything about hydrogens, protons, alkanes, but it tells us very little about functional groups that don't have hydrogens, functional groups that are very prominent by IR. So just to correlate the protons in the structure to the spectrum before we end, the methyl group next to the carbonyl gives rise to the signal at 2 ppm. The methylene next to the oxygen gives rise to the signal at 4.5 ppm. And all of the aromatic protons indicated here with C give rise to the overlapping or the large signal around 7 to 7.5 ppm.